Hello. Is that coming through okay? 1, 2, 3.
All right. Our next speaker is Fraser Tweedale, who is also a Red Hatter coming from Australia. Fraser is working on free IPA project, and he'll be speaking to us about property-based testing on write, and he'll be using Haskell for that.
Okay. Hello, everyone. Yes, I will be speaking about property-based testing today. So, as you heard, I'm a developer at Red Hat, and I work in Brisbane. I work on the free IPA identity management solution and the dog tag certificate authority. So at work, I'm mainly using Python and Java, but outside of work, I mainly use Haskell, and I like it very much. So today I'm going to introduce property-based testing and motivate it with some examples. I will be demonstrating the concepts in Haskell using the QuickCheck tool, but we will take a brief look at property-based testing in other programming languages. And finally, I'll be concluding the talk with a discussion of the limitations of property-based testing and a brief look at some alternative approaches. So property-based testing gives you a way to state algebraic properties of functions that must always hold. It also gives you a way to declare how to generate random values of your types so that the testing tool can generate these values and use these values to check whether the property holds. They will usually provide generators for most of the common types in the standard library of whichever language it is that you're doing this in. And so finally it will, having been able to generate random values and having a set of properties to check that those properties hold in a large number of cases. That number's typically configurable. 100 is a common default. And if the property holds in all those cases, then the test is declared to be successful. So this is great for checking laws and invariants of algorithms, data structures, and abstractions that you're using in your code. Basically everything, every function you use, every data type you use will have laws and invariants associated with it. Property-based testing makes it really, really easy to test whether those invariants hold. Or, alternatively, if it can falsify your properties, it will give you the counterexamples that it was able to find. It's also good for testing code against model implementation. So, for example, if you have a selection sort, you could arguably say that that is a model implementation of a sort. Then maybe you write a quicksort or a heap sort. It's very easy to state a property that says that the behaviour of your quicksort is the same as the behaviour of a selection sort, or in more precise terms, that these two functions are observationally equivalent. Finally, properties are also meaningful documentation. If you have a complete set of properties for your function, no one has to look at the code to understand what that function does. And furthermore, people can use these properties to reason about the behaviour of the code in the context of a larger system. So where they're using that code, they can take those properties and, in logical reasoning sense, combine those properties with other properties to determine the behaviour of a system as a whole. So we'll go straight to some examples now. And I'll just take a seat because there will be live coding. So this is Haskell. This is simple Haskell, but if there's something that you don't understand, please just shout out, and hopefully I can give you the understanding you need to make sense of this code. So this is a function called rev, which has the type list of A to list of A. So it takes a list of some type A and returns a list of some type A. There are two function bodies. So the first one, we pattern match the input, and if the input is an empty list, then this is defined as the empty list. If the input is a non-empty list, we have destructed the value to the first item on the list and the remainder of the list. We recursively call reverse on the tail of the list and then append a singleton list containing the value that was at the head of the list to the end. So this is an implementation of a list reverse. The type of the list reverse, however, does not fully constrain the implementation. A function with this type could do many things. It could simply return an empty list, or it could return, say, the first element in the list just repeated a certain number of times if the list was non-empty. So there are lots of different things it could do. There are two properties that uniquely specify the reverse of a list. That is, that the reverse of a singleton list is the same list, and that given any two lists, so for all x's and for all y's, that the reverse of those lists appended together is the reverse of the second list prepended to the reverse of the first list. These are just comments, by the way, if you weren't aware. Okay, so we can use QuickCheck to state properties and test properties about this function. So the first property, prop_rev_unit, takes a single integer. So in this case, we actually have to specify a concrete type that QuickCheck can use to generate random values, and returns a bool. So this function, with the single argument x, is defined as the equality of the reverse of the singleton list containing x to just the singleton list containing x. Similarly, for reverse append, here we have two arguments, each of which is a list of integers. These arguments are specified on the left-hand side of the equation here. And we simply state our property. So the reverse of x's append y's is equal to the reverse of y's append the reverse of x's. Okay, So is everyone clear with what these functions are stating? Okay. So in the GHCI REPL now, I've loaded up this module, so we can just call QuickCheck prop rev unit. So, okay, passed 100 tests. So QuickCheck has just generated 100 random integers and used those random integers to check this property prop rev unit, which is this first property here. Similarly, we can QuickCheck prop rev append. It says, okay, passed 100 tests. If we introduce a bug in our list reverse, and reload the file, prop rev append is still going to hold, but now prop rev unit is falsifiable. So you do need to test all the properties, but you can see that this is a very succinct way to state what the behaviour of the function should be, and it's very easy to just call QuickCheck on that to test. So that's the first example, reversing a list. A slightly more complex example is coming right up. So if we have here a simple sum type for an expression tree where we have literal integers, two sub-expressions being added together, or two sub-expressions being multiplied together. So this is just a simple algebraic data type for constructing an expression tree. We can define the function elim mul1, which takes one expression and returns an expression. So it does a transformation on this expression. What we want this function to do is to eliminate in this expression any cases where something is multiplied with the literal 1, which of course is the multiplicative identity. So the value of the expression should not change, but we can simplify it. So in the case where the input expression is the literal x, we just return literal x. If it's an add expression, then we just perform the elimination on both sub-expressions and reconstruct the add. If it's a mul expression with the literal 1 on either the left or the right-hand side, then the result of simplifying that expression is just going to be whatever the non-literal one side of the expression was. In this case, elim mul1a for both of these patterns. And finally, if it's a mul expression without a literal 1 on either the left or the right sub-expression, then we simply perform the elimination on each of the branches and reconstruct the mul. So is that clear to everyone? Okay. So we can state a property here that will check that the function elim mul1 does in fact eliminate all of these cases from the tree. If we encounter a case where we have a mul value with the literal 1 on either sub-expression, then that property is false. If it's just a literal something, it's true. And if it's a mul expression or an add expression as long as it's not a mul with the literal 1 on either side, then we simply check that both sub-expressions have this property holding for them, and then it's just a logical conjunction. So we just AND the result together. So if we now quick check this property, prop elim mul1 elim. I think I need to reload this. Okay. So we have a problem here. It says no instance for arbitrary expr. So we haven't actually told QuickCheck how to generate arbitrary values of the type expr. So I'll show you how to do that now. So we say instance arbitrary expr, so it says we're going to create an instance of the arbitrary class for the expression type. We'd say arbitrary is sized gen where gen 0 is one of So what size does is, if you're generating a recursive data structure, it introduces a dimensionless integer value that you can reduce to make sure that you don't construct an infinite data structure, which can actually be very useful, but they're quite difficult to evaluate. So in the case where we reach 0, that tells us we need to make a leaf. So we just say that an arbitrary expression when we're at a leaf is going to be one of an arbitrary literal, or just the pure value literal 1, just to make sure that we have a reasonable number of literal 1s in our expression tree. If it's a non-zero value, then we need to reduce that. So we just say let n prime equal n div 2 in one of. And this time, being not a leaf, well, we could still have an arbitrary literal value here. Or we could have an add value applied over two arbitrary sub-expressions. Similarly, a null value applied over two arbitrary sub-expressions. Now we can reload and run QuickCheck, and you can see this time QuickCheck does run. It's able to generate the random values, but in fact it's falsified the property, and there's a subtle bug in my implementation. However, you'll see that this is quite difficult to work out what's going on here with the counterexample that's found. So we can, in fact, simplify the counterexample. So just going to remember the name of the function. It's shrink. So if we have an add expression, we can shrink that. So just find possible ways to simplify the expression that will help QuickCheck try and reduce that to a minimal counterexample.
Sorry, could you mind scrolling down a little bit?
Yeah, sure, that's fine. Okay, so if there's an add expression, a shrink of add would be, for example, the list just A, just B, so we're stripping off the add and just returning either the left sub-expression or the right sub-expression. Or we can recursively shrink on A and B and return an add. So in this case it will be add shrink A, shrink B. So same for null, and then any other thing will just return an empty list of shrinks. Okay, so now we reload the expression, we get a much simpler counterexample reported. And in fact, the problem is where we have a null inside a null, where that null has two literal ones. So the inner null is going to be simplified to a literal one, and then that literal one is going to appear in the outer null expression. So we can fix the bug simply by examining the output of this expression. And if it is now a null lit1a or a null a lit1, then we have to recursively call a libnull1 on the non-lit1 sub-expression of the result of this expression. So we libnull1a. Same here, and then if it's anything else, we can just return that expression. Okay. So if we reload now, run the property again, and finally we have a passing test for this property. So hopefully you can see that QuickCheck can be quite useful in finding subtle edge cases, and it relieves the developer of the burden or the cleverness required to work out what edge cases are going to cause the function to perform incorrectly. But rather you just state what the properties should be and allow the property-based testing tool to generate lots of random values in order to determine whether the properties hold in a large number of cases. Okay, so there are a few gotchas. The first one is exhaustion. So if we consider this property given a list of integers with the precondition, and that's what this arrow function does. So with the precondition that every value in that list is even, then we should be able to, for every value in that list, divide it by 2, then multiply it by 2, and that should give us the original list that we had. So for any list of even numbers, if you divide all those numbers by 2 and multiply them by 2, you have the same list of even numbers. If we try and check this property, even, half, then double, we have a problem. QuickCheck gave up. It only passed 63 tests. The problem is that it's generating lots of random lists of integers, but this precondition is not holding in a large enough number of those cases to execute this test a sufficient number of times to satisfy the tool that the property holds. So the way to work around this is simply to define a new type which we'll call evenList and provide an instance of arbitrary for evenList that doubles every number in its inner list before wrapping it in evenList. So this is going to ensure that any arbitrary evenList only comprises even numbers. This is the same property, but instead of having a list of int, it's got evenList int. So if we test that property, you can see that QuickCheck is satisfied. So, recap on exhaustion, that naive use of preconditions can result in not enough test cases to satisfy the tool. The solution is either to use a custom generator to ensure that the precondition is satisfied, or ideally to redesign your data types so that the precondition is an invariant of that type. Okay, the next gotcha is trivial data. So you could be generating lots of random lists, but they might be very short lists. You might want to be able to ensure that your property is being checked with long enough lists. So it's a decision that you as the programmer have to make as to what is an appropriate distribution of data in order to satisfy you that the property holds. We can use the collect function or the cover function to examine and report on the distribution of the test data that the tool is generating. So if I just run these functions now, prop, right, list all even, you can see this time it's actually fully reported the distribution of the data. So in 52% of the test cases, 52% of the cases tested by QuickCheck, the length of the list was 0. Yeah? Sorry, you can't see the first column? Oh, okay, sorry. That's 52%. So in 52% of cases...
Maybe if you slightly narrow the window.
Yep. Okay. How's that? Okay. So in 52% of the cases, the length of the list was 0. So there's a lot of trivial cases in this test. If we have the cover example, it says, okay, every test passed, but only 40% of the test cases were non-trivial. So we've given the threshold here that to be considered non-trivial, the length of the input must be greater than 1. So zero element or single element lists, we the programmer have decided are trivial. So in this case, it does report, yes, every example passed, but with the caveat, many of them were trivial cases. So recapping trivial test data, the trivial test data can result in tests passing vacuously. You can use the collect or cover function to inspect distribution, and you can use frequency to control the distribution. So if I return to the arbitrary instance for even list, instead of one of, which uses all of the possibilities with equal distribution, we can change this to frequency and just introduce a relative frequency here for these expressions. So if we say 1 time out of 8, we'll produce the empty list, and 7 times out of 8, we'll produce a non-empty list. So now if we rerun this test, this time there is a sufficient number of non-trivial test cases to satisfy the tool. Finally, with infinite data, and I did allude to this briefly earlier, if we have an arbitrary instance where we do not use sized, if I were to try and generate data using this instance, my computer would lock up and I'd have to kick it in the head because it would just expand out, use all the memory very, very quickly as it tries to evaluate this in what is likely to be an infinite data structure. So in this case, we use the size gen with the dimensionless value here, which we ensure that we reduce every time we recurse, so that eventually we reduce that number down to 0, and we use that basically as a sentinel value to say, okay, it's time to generate a leaf, no more recursion. Okay, so the infinite data structures, they are useful, very useful in fact. Many kinds of problems are solved very elegantly if you have a lazy language where you can use infinite data, but you have to be careful what you evaluate. If you try to evaluate the whole structure, well, you won't. Your computer will not be able to do that. Maybe quantum computers can do that one day. I don't know. Okay, so in other languages, most languages have at least one implementation of property-based testing. There's an incomplete list on Wikipedia, so if you just search for QuickCheck, it has a list of a whole bunch of clones and similar tools. But it's not an exhaustive list. There are some implementations that, to me at least, seem quite nice or quite reasonable that don't appear on that list, although I suppose I could go and add them. It is Wikipedia. So these include one called Pixie for Python, or the functional Java test module. If we have a quick look at a Python example, so you can see that the way that the tests are stated is quite similar to QuickCheck. So we have a QuickCheck decorator here for Python, which basically tells it, hey, this is a test where you're going to have random generation. We have the name of the test, a parameter whose default value is a generator. This generator is provided by the Pixie library. And then you simply assert the reverse of the singleton list is the singleton list. Similarly, for proprev app, this time we have a generator for a list of int, and similarly for the y's parameter. And the assertion, the same assertion we were making in our earlier test, that the reverse of x's plus y's is the reverse of y's plus the reverse of x's. And so we can run this test, and you can see proprev unit passed 100 tests, proprev app passed 100 tests. So the property holds. Here's a Java example using JUnit QuickCheck. So the type signatures for our reverse and append functions are as on the slide. So we're using Java generics. over the type A. So for any type A, the reverse of the list A is going to be of the type list A, and the append of the list A is, the append of list A X's and list A Y's is going to be a list A. So those are the type signatures that we're dealing with. There's a bunch of imports, and you have to run with the JUnit theories class, and then you state your properties. A fair bit more verbose than in other languages, but that's Java for you. So for RevUnit, we have the for all annotation for the argument, which is an integer x. So this tells the framework to use the JUnit QuickCheck generator to supply the values for these theories. And then in the body of that function, we create a new array list with a single element, and then call reverse on that and assert that that is equal to the input. And again, with reverse append, much the same as you've seen in the earlier examples, we take the two lists, x's and y's, and we assert that the reverse of the append is the append of the reverse of the arguments flipped around. Okay, is that example clear to people? Yeah. Does anyone have no idea what's going on? Okay, I did actually run these examples and they work. The error reporting is not very nice in the Java example though. Okay, so limitations of property-based testing. You can have bugs, just like any other kind of test. So you could specify an incorrect arbitrary instance, for example. You could specify your properties incorrectly, or something that's unique to property-based testing, you might have an incomplete set of properties for your data type. So you might have properties that are correct, but they might not be enough properties to specify the full behavior of your type or your abstraction or your function. So you do have to do, in some cases, some deep thinking to work out, okay, I've specified some properties, the properties are passing, but have I specified enough properties, or are there properties I haven't specified that could be causing bugs to go unnoticed? Sometimes randomness isn't enough. So if we consider this property with password hashing and verification, so prop verify EQ with a single parameter s, which is a password, we state that the property is that the verification of s against the hash of s is true. So if you hash a password and then you verify the password against that hash, that should always work. The opposite property of that is to say that for any two passwords that are different, verifying password 2 against the hash of password 1 should always fail. So basically you can't log in using someone else's password. Okay? We have the precondition that s and s prime, the two password arguments, are not equal. And then we say that the verification of the second password against the hash of the first password must be false. That is a perfectly reasonable algebraic property, but QuickCheck will probably never ever tell you if you've got a bug in that. For example, if hash truncates the input before hashing, it's very unlikely that you're going to get two random values, s and s prime, that share a long common prefix. So some bugs are unlikely to be found with random data. The way to work around this is to mutate or fuzz the data in a way that's relevant to the domain, but this implies that the developer is clever enough to know what they have to do to trigger the sorts of bugs that you might get in a particular domain that randomness might not catch. So to solve the problem here, there's a function fuzz, which takes a password and returns a generator of new passwords. And prop verify fuzzed, you can say for all the fuzzes of s, verify that verify that prop verify not equal holds against s. And failure cases. So arbitrary instances are great for generating random valid data, but how do you specify the behavior if the function is given invalid data? Basically, example-based testing is the way to go with that. So for this example here with JSON encoding and decoding, a good property to specify would be that to dump a value to JSON and then load it back in should give you the same value. However, the behavior of a parse function on invalid data, well, you don't have a way to just generate arbitrary invalid data, so you might just use an example-based test. So in conclusion, property-based testing is true automated testing. It lets you do more thorough testing in less time, which means less money, and it relieves the developer of the burden of finding and manually writing tests for the corner cases. Properties are also meaningful documentation. Users of your libraries will thank you for stating the properties and for testing them. So the best test data is random test data, but a bit of domain-specific non-randomness is sometimes useful, and example-based testing still has its place. So I promised we'd look at some alternative approaches. One alternative approach is exhaustive testing. So the catchphrase there might be the best test data is all of the data. So in exhaustive testing, you check that the property holds for all values, or in some cases, if you're dealing with recursive data, all values up to a particular depth. This also supports existential properties. So instead of saying, for all x, some property, you can say there exists some x for which this property must hold. And exhaustive testing is available in several languages, including Haskell, Scala, C++, Python, OCaml, probably some others. And then there's proof. So the best test data is no test data. Don't worry about test data, just prove that the function is correct. So some languages have theorem-proving capabilities. In these languages, properties become theorems, and if you can't supply a proof for that theorem, then you don't get a program. It's usually a compiler error. These languages sometimes support extraction to mainstream programming languages like Haskell and OCaml, but also JavaScript and C. And you can also use proof systems to prove the completeness of a set of properties. So I mentioned a little bit earlier in the bugs slide that, maybe you've got a lot of properties and they all pass, but how do you know you've got enough properties to cover the behavior? Well, you might be able to prove that. And there's a link on this slide to a completeness proof for those two properties that we've looked at several times today for the list reverse. So it's proof that those two properties are in fact complete. Any function that satisfies those two properties has the same behavior as a model list reverse function. Okay. So I was going to show an example of a proof, but I might skip that and just have time for questions. But briefly, here are some resources. So there's the original paper by Hughes and Klassen from 2000 about QuickCheck, which explains how this actually works in Haskell and also talks about the motivations for doing it. There's a blog post by Tony Morris. It's entitled Automated Unit Testing Your Java Using Scala Check. It does show you how to do that, but it also talks about some of the principled reasons why this sort of testing is a really good thing to do. So things like doing property-based testing pushes the developer along the path of forming logical theorems about their programming, and that this is actually an essential part of what we ought to be doing as programmers, in Tony's opinion. So I'd encourage you to read that post. There's a UC San Diego lecture on QuickCheck, which is, I think, probably the best introduction to QuickCheck in Haskell that I've seen. There's a talk by my friend Dave Lane called QuickCheck Beyond the Basics, which shows you how to QuickCheck monadic or effectful code, so code that isn't pure in terms of just having one input and one output, but code that has some effect in an environment, and how to use QuickCheck to test effects in environments. And if you're interested in learning more about Haskell, this link on the GitHub there is a learning path that I would recommend. So thanks for listening. The slides are on GitHub. There's a feedback link there as well if you'd like to give feedback to the talk, and my email and Twitter. And now there is time for questions. Yeah, Sina.
How applicable is this to very complex language, like Persian and many smaller languages? What is your advice if you want to try to use property-based testing on very complex languages?
Yeah. I've never used QuickCheck to test kind of complex systems of code. So I'm sure other people who have probably tried to do it would have an answer for you as to whether it's a good idea or worth doing. The nice thing about it is that you can compose the reasoning. So when you have these theorems or these properties and you know that they hold because you've tested them with QuickCheck or proven them, then you can use these to build up reasoning about larger or more complex systems, and I don't see any reason why you wouldn't then be able to derive theorems about the behaviour of the composed system that you then could check with QuickCheck. Yeah?
Maybe similar question. Looks like it's perfect for functional languages.
Mm-hmm.
What about languages like C++, where there's a lot of global state, or well, you cannot ensure you don't have a global state?
Sure.
Please repeat the question.
Oh, yes, please repeat the question. Sorry, so the first question was about QuickCheck for complex code, larger programs, etc. This question was about what about other languages where you have global state, for example. My advice is don't have global state in your programs. You actually don't need it. Like that's a fact. The Church-Turing thesis says so. So yeah, I would if that's your situation, if you have code that you know is pure, then you can start using property-based testing today. But I think it would also be good if you could work towards removing the global state from your program, because that will be a big win as well. Okay, so I'm out of time, but I'm happy to continue discussing this with anyone out in the hallway who is interested. Thank you.